Okay, so at the end of the previous lesson, we said that there was a method of measuring nearby stars, but the limit of that method was about 150,000 light years. Knowing that our galaxy is roughly 100,000 light years apart, essentially that method, which was the Gaia satellite launched in 2013 with a precision of 20 micro-arc seconds. If you didn't watch Friday's lesson, you'll have no idea what that means. It means that that precision of measurement gets you to a distance of 150,000 light years. So the early astronomers were kind of stuck because they couldn't measure anything further, okay? So here was the problem. We couldn't figure out how far anything was beyond 150,000 because if you looked at it 6 months apart, there would be no parallax effect because it's just too far apart. It's like putting your thumb on the other side of the oval and then opening your left eye and your right eye. That thumb ain't moving. The closer your thumb is to your eyeballs, the further it's going to appear to move. The further away, it moves less. And they're saying that obviously at some point, we just don't know how far away something is. Here was the issue. Stars have an intrinsic brightness, and that is a measure of their actual intensity. Actual intensity. Okay? However, all we are able to measure is their apparent brightness, how bright they appear in the night sky. And that is what we can measure. Okay? So, the problem is, the further you get away from a star, the less intensity of light that reaches us and the duller it appears. So, consider that you are trespassing on the school grounds at night. It is pitch black, there is no light, so you have to use your imagination. Security guards rock up, maybe the police, and you're out on the oval trying to evade them. A policeman has a torch, and you see this torch glowing on the horizon, okay? Now, you do not know whether it is a 100-watt torch that is 10 meters away from you, or if you double the distance, then maybe it's a 400-watt torch that's twice the distance. You might have learnt last year that intensity is inverse proportion square, okay? And so you might have remembered I1 on R1 squared equals I2 on R2 squared, okay? So if you double the distance, you're getting a quarter of the intensity. So maybe if the security guard, maybe there's two security guards, and you suddenly see two lights in the sky on the horizon. You're like, crap, they're onto us. They seem to look the same brightness. They have the same apparent brightness. But maybe one of the security guards is 20 meters away with a 400-watt torch, and the other bloke's closer with a 100-watt torch. Okay, that was the problem. And it's not until you get tackled by security and when you're lying on the ground, you happen to look on the side of the torch and it says P equals 400 watts. You can go, aha, that's right, you must have been 20 meters away when I observed your torch, okay? And that was the problem. We cannot go to the side of the star and look at the power rating on the side of it and see that it's so many watts, okay? So what was needed was a standard candle. They were literally called standard candles that astronomers could use. And they found a really useful star. They were called Cepheid variables. Cepheid variables are stars that wobble. In fact, they pulse in and out. They are not really stable in how they burn. Our star is a nice constant star. Yeah. Some stars appear to glow brighter, then duller, then brighter, then duller, then brighter, in a nice regular period. And in fact, there was a relationship that the brighter they burnt, the longer the period of the pulse. Okay? So, as it says there, the brightness directly proportional to the period. And so all you needed to do was measure the brightness, and you can Google search these pulsings of intensity over time. And this could be sometimes days or even weeks. I mean, sometimes, let's just say, I don't know, oh gosh, this is a bad graph. Let's say 20 days. Okay, this pulsing varied sometimes from a few days up to a few weeks. The longer the period, the brighter the star. And so, they used this Cepheid variable to, once you knew the period of the star, you could figure out its intrinsic brightness. And then, boom, you can compare its intrinsic brightness with the apparent brightness, and you know how far away that star is. It's like saying, if you can figure out what the power rating is on the side of the security guard's torch, then you can view it from anywhere at night and you know exactly how far away they are. You're just comparing the intrinsic power with the apparent power, okay? And in fact, don't draw this, but in the early days, there was only one known Cepheid. And so the data looked like this. And so there was only like really a medium correlation. And then further astronomy, they said, hang on, there's actually two types of Cepheids that are slightly different. And then they went, okay, so this data here belongs to our Cepheid variable 1. And then boom, nice and correlated. And this data here relates to our Cepheid variable 2s. Again, a bit nicelier correlated. Okay, so that's the story of the Cepheid variables. And so obviously you think, you're doing your work on this, and then 5 years later somebody finds out something new and you're like, crap, I've got to go back to my data and basically rejig the maths, and my uncertainty reduces and I become more confident with my measurements, because that's the whole thing about science. You're relying on other people's work to then advance your own. Okay? So there's Edwin P. Hubble. Over the page, please. So, Edwin used the Cepheid variable stars to figure out how far away they were. But then he also needed some other information about the star. And so, you should know this from year 10 and possibly year 11 physics. Basically, the Doppler effect is the apparent change, it is the change in wavelength due to the relative motion between the source and the observer. And obviously, you can be moving towards the source, or the source can be moving towards you. That's the whole thing about relativity. It doesn't matter as long as one is moving towards the other. So here's our little diagram here. Blue shift and red shift means you're moving towards. Red shift means it's moving away. Okay? So let's just quickly draw a box traveling with a certain velocity. And this box is emitting light. Okay? Now, a person over here would see that light redshifted. The wavelength is stretched out because in a given period of oscillation, the easiest way to explain it is in a period of oscillation, the inverse of the frequency, that object has moved v times the period. Okay? Or v on it. It's shifted forward. So in that time, the wavelength is now acting over a longer distance. So if the wavelength is now spread out over a longer distance, the wavelength gets larger. Okay? So this person would see a increased wavelength. But remember Einstein, he still sees that velocity as the speed of light. All right? So it's not traveling at him any slower. The person over here that's approaching, again, have a think. In a given period of oscillation, whatever's producing this jiggle, it's moved forwards a certain distance, vt, and so the wavelength is now only acting over a shorter distance. Okay? So like ct minus vt kind of stuff going on there. So we would see a shortened wavelength. Okay? Wavelength decreases. Again, same deal. This bloke would still go, no, I'm still observing this light traveling to me at the speed of light. So, if our star or a galaxy is traveling towards us, we would say that the wavelength decreases. It's shifted towards the blue end, and we say it is blue shifted. Okay, and I should have done that all in a blue pen. And if it's receding from us, we say that the wavelength increases towards the red end. We say it's been red shifted. Now, red and blue, just remember that's the either end of the visible light spectrum. So they've just chosen how it would affect visible light. But remember, this occurs for all regions. So a star could be emitting UV. And so if it's traveling towards us, it's going to be a shorter UV wavelength with a higher frequency. Yes, Callum?
Why blue shifted and not violet?
I don't know. Blue and red, those were nice contrasting colours. You're absolutely right. And why blue and red? Why not radio shifted and gamma shifted? Because really, those are the two extreme ends of the entire spectrum. They've just chosen the two ends of the visible spectrum. Okay? So, you might recall from year 10 that you can use this to figure out a lot of stuff about stars. So let's look at the emission spectra. Spectra of an object. Now this could be some imaginary atom that has 4 bands in the visible light spectrum. And we'll say that when we measure this, we are at rest with the object. In a lab, we're generally stationary. So all of this on the spectrum chart, these have been measured in the same reference frame. All right, I am at rest with the spectrum and I measure it and we get these bands. Okay. Now, if a source was to be moving either away from us or towards us, then those bands are going to be shifted. So if we just trace down beneath here, you might be able to see that these have all been shifted. And they should really be all shifted by the same amount. Okay? And we can measure that change in wavelength. And on this spectrum, we've got red side and we've got blue side. We see that the wavelength has decreased. No, it hasn't. It has increased, sorry. Because remember, over here we've got like 700 nanometers. Down here we're at about 380 nanometers. So really, it's going that way. The wavelength is getting smaller. Okay? Cool beans. So, there is an equation that relates the shifting. It's V on C equals delta lambda on lambda, stationary. Stationary. S for stationary. This obviously breaks down. Let's just write only works for V less than 10% the speed of light. Okay. Because have a think. If I gave you, let's say I gave you a wavelength that was really small, let's say 380. Let's say we're right at the edge of violet light, a nice violet light. And then this object moves away from us such that it shifts all the way down here to 760. It gets shifted all the way to red, 760. Okay? Using that equation, your change in wavelength is 380 divided by 380. That would imply that your recessional velocity is the speed of light. And in fact, any more shift, let's go to 800, then our fraction, the change in wavelength, is now greater than the original. You're going to get a value greater than c. So this equation, back in the 2014 days, when we didn't worry about Lorentz factors, you would only be working with relativistic values. Turns out, stuff is travelling faster the further away from us, and so we do have to take relativity into account. Over the page. This could be waste spec here. Okay? So, let's just have a look at this. An astronomer notices a calcium emission, generally stationary, is 464.010. But it's been observed, there you go away, it's been observed that the object is moving. It's been shifted. And in fact, we've got an increase in wavelength. The object has been redshifted. So we'll just write that down, red shift. So, again, this equation is not in the data sheet, but the effects of Doppler is. All right, so you should be able to explain the Doppler effect and its effect on light, blue shift, red shift. Boom, there's an equation, we throw it in, use it. It's not that tricky. So, let's have a look here. You could figure out V equals the change in observed wavelength over wavelength times C. Let's do it all on one line. So we'll go, it doesn't matter which one you use. You know, you could assign a convention, negatives and positives, but let's just go, absolute. So 465.34 minus 464.01 over 464.01 times by 3 by 10 to the 8. Okay, so let's just have a quick look. That's just over 1 nanometer. It's 1.3 nanometers divided by 400. So it's less than 1% the speed of light. Okay, it's 1 by 400. And so you spit it into your calculator, you get 8.60 times 10 to the 5 meters per second. And we might want kilometers per second, so let's just divide both sides by 10 to the 3. Okay. This is a more common term. Astronomers generally talk about the recessional velocity or the advancing velocity in kilometers per second rather than meters per second. Now, you will notice I need to put the good old purple stamp of not in syllabus here. For relativistic speeds, have we all got that written down? Yeah. So let's go to a question now where we need to take relativistic speeds into account. Okay? Again, not in the syllabus, but a really nasty waste exam maker might put this in to see if you nerdy kids can solve. Okay? So, again, don't worry if this is not making sense to you. Let's have a look now. Spectral emission from calcium is observed to be now 322.14. So we're going to take the same, but by the way, we're using the same lambda S, okay? So 464.01. If we just use that non-relativistic equation above, then we're looking at a change in wavelength of like 140. And 140 over 460 is, you're going to be getting up to like one third the speed of light. Doesn't work that way. Relativistic effects have to be taken into account. The maths is a bit tricky, but you're all good to do that. Let's have a go. Let's use the maths. 322.14 over 464.01 equals square root. Now, I'm just going to say for now, V on C, let's just use the symbol beta. You might have seen it in some textbooks, they just use the symbol beta. It's the ratio of V on C. Just to make the maths... No, you know what? I'm just going to stick with it. Let's just go 1 plus V on C over 1 minus V on C. Now, what I'm going to do is square both sides. Yeah? If I square both sides, that fraction becomes 0.482. Then I'm going to multiply both sides by the denominator. Then I'm going to expand out my terms. Then I'm going to put my V on C's on one side and my numeraries on the other. And then I'm going to divide my V on C's by the coefficient. And we get negative 1.05 by 10 to the 8 meters per second, or 1.05 by 10 to the 5 kilometers per second. Now that gives us the now I did ignore there is a negative there, and maybe if you're so inclined you could go and see if I shorten. Wait, try again. If I increase the observed wavelength, then maybe that becomes a positive. So maybe there's a sign convention in there that a negative means it's travelling towards us because it was blue shifted, and maybe a positive means it's receding from us because it's red shifted. But I'll leave that to you as an activity. But what you would need to do is go, our object, the wavelength was seen to decrease, which means it's been shifted towards the blue end, hence it's travelling towards us. Okay? At, that's what? It's less than 30% the speed of light. And I think if we use the non-relativistic, we're up towards 40% the speed of light. So it does, remember, this equation here, that's your Lorentz factor, and that sort of puts the rules in place that we can never get a velocity greater than c. Okay? All right. Over the page. This should have been probably before that. This should have been up with the earlier images. But you can get some really cool applications of this. Have a look at this image over here. If there is a distant star and there's an unseen planet, obviously planets don't emit light, they can only reflect. It might be so far away that we can't actually see any light being reflected off that star. But what we can do, and the next problem is, sometimes if the planet goes between the star and us, we could see a drop in intensity of light from the star. So you're watching the intensity and there's going to be a tiny shadow. So there'll be a drop in intensity. And so you can measure the period of the drop in shadow. And in fact, that was in the 2016 WACE exam comprehension section. Have a look for it. But maybe the star and the sun and the planet are not in the same plane. So I'm in the plane of Campbell Baird right now, and maybe the planet is tilted in a different plane. And so it's never going to get in between me and Campbell. So there's never going to be a drop in light. So what they can do is realise from your Kepler's laws is that these two objects are not orbiting the star, it's orbiting the centre of mass of the two-body system. And so the centre of mass is going to be in the centre of that white circle there. Okay? Centre of mass. And so the planet is going to do a little bit of a wobble. And the wobble is going to be the period of orbit. And whilst it's wobbling, it's then going to be travelling away from us for half of the time and then towards us for half of the time. So when it's travelling away, the light is going to be red shifted. And when it's travelling towards, it's going to be blue shifted. And it's going to be, the change is going to be sinusoidal. There will be a maximum blue shift. Negative toward, maximum blue shift towards us, maximum red shift away from us. So look at that. All you do is you plot the wavelength, you calculate the velocity away towards, and then you can find the period. Okay, the period variation tells us that it has an unseen planet, and then the velocity change can tell us the planet's mass. Because it's easy to tell the mass of a star. You look at how bright it burns and the peak wavelength, the temperature at its surface. It's easy to figure out the mass of a star. Okay, and so if you know the mass of the star, then the unknown is going to be the mass of the planet, but they're linked by the period of revolution, which is quite cool. So this is an application of redshift and blue shift. Okay. You can also get, watch you here, you can also get galaxies. Obviously galaxies, generally there's a black hole at the center, and most galaxies are kind of, oh dear, that doesn't do that. Most galaxies are spirals, okay? And so we've got, 100 billion stars all sort of spinning around like that, and then 100 billion stars all spinning around like that. So you can have one side of the galaxies traveling towards us with a velocity, and then one side might be traveling away from us with a velocity, okay? And so then you can see, well, this side's going to be blue shifted to us, and this side's going to be red shifted to us. And obviously, you'd have to have a precise enough measurement that you could look at one side of the galaxy to the other, which you can. I mean, you can see through a telescope, there's one nebula, there's a few nebulae that we can see. There are a few galaxies that we can observe in a telescope, so you can take measurements of one side compared to the other. By the way, the bulk of the stuff in these stars is just hydrogen and helium. So all you're really looking for are these two bad boys here. And you go, well, are they shifted left or are they shifted right? And by how much are they shifted? Okay? So, just at the bottom of this, before we go to Hubble, who is our Lord and Saviour of this booklet, this use of emission can tell us a whole heap of stuff. We can figure out temperature and pressure. By using Wien's law of displacement, you can calculate the maximum wavelength or the peak wavelength of the black body curve. You can figure out its temperature. If you can figure out the size, you can figure out its pressure. If you know its size, you can figure out its mass. By looking at the shift in emission spectra, or by looking at the emission spectra, you can figure out the elements that it's made of, because each element has its own unique spectra. By looking at which way it's shifted, you can figure out its direction, I should say. And last one, by figuring out how much it's shifted, you can figure out its speed. So all of this, because that's the thing, the only thing that we can observe from a star is the electromagnetic spectrum that it's shooting at us. That's it. We can't hear it, we can't smell it, we can't go up and measure it with a tape measure. All we can see is the photons of light that are coming down. But those photons of light have an incredible amount of information that astronomers can then run away with. Question?
Yes. So why then, before this kind of knowledge had become widespread in science, when they were looking at determining the composition of stars,
Yep.
What did they just think there were a bunch of new elements they hadn't discovered?
Yeah, so that's how they found helium. So Hubble was sort of around the 1930s.
Because it's been redshifted slightly, they see like, they might measure 100,000 stars and be slightly different wavelength and all of them.
Yeah, and so the Doppler effect was sort of made known by that German dude in the late 1800s. So they were piecing it together. It wasn't until, so they knew about spectroscopy in the 1800s, but they couldn't explain it. And it wasn't until Niels Bohr that came and said energy levels, discrete levels, unique to each atom. Okay? So, here's where did Hubble go? Hubble pieced these two bits of information together. Okay? So he used the Cepheid variable method to measure distance. And he used, why did my method get obscured there? What's going on? Can you see that? Okay. And then he used the Doppler shift to figure out the velocity. But he could only use the Cepheid variables. Remember, the Cepheid variables were the stars that pulsed. But turns out if you look in enough galaxies, you'll find Cepheid variables. Okay? And you could just observe their pulsing. He found a remarkable pattern, and the pattern is here. The more distant galaxies had greater redshifts. In fact, what was more remarkable, it was directly proportional. And this has become known as Hubble's law. Okay, so here is a graph that I have borrowed. You will notice the distance to the galaxy is in megaparsecs. A parsec is 3.26 light years. So we are looking at galaxies beyond our own. That's 100 times 3.26 million light years away. So this little dot here is 326 million light years away. Okay? By the way, I'll tell you now that your brand new 2019 datasheet gives us the two conversions that we calculated on Friday. Okay? So if you go back to the bottom of, I don't know, page 2 or 3, it gives us, in the datasheet, it gives us a light year in kilometres. For some reason, kilometres, but before we figured it out as 10 to the 15 metres. And it gives us 1 megaparsec as 3.26 mega light years. Okay? So here's the thing. Oh, don't do purple. That's not the right. Let's just go blue datasheet box. Here's the thing. We can calculate, if we had 10 minutes, we could use the mean Earth-Sun distance and figure out the parsec, which is the distance you need to be such that the subtended angle of 1 arc second has a baseline of 1 astronomical unit. We did that on Friday. I'm trying to scare the kids that weren't here. We could then convert, we could find out a light year, we could figure it all out. But they've said, well, we don't want kids in the waste exam spending 15 minutes trying to calculate these astronomical conversions. So here they are here. Okay? So, a megaparsec, 3.26 million light years. All right? So, let's just, the accepted value is at around 71, but let's just let's see what we could do. In year 10, I always give my students let's go 500. That's a bit of an easier number. The gradient. All right, so your delta y, 500 megaparsec, and then your delta x. Oh wait, crap. What have I done wrong? Your delta x is 500. Sorry. Your delta y, I'd probably go, I don't know, about 31,000 kilometres per second. So this is a good activity to give my year 10s. You could go, the gradient equals 31,000 over 500 megaparsecs. 62 for this graph. 62 kilometres per second per megaparsec. So, I mean, this is a very weird unit. What this means, for every 3.26 million light years away a galaxy is, it seems to be receding from us at 62 kilometres per second. You go another megaparsec away, another 3.26 million years, that galaxy is now double that, 124 kilometres per second. Recession. And please recall, it's all recession. Some nearby stars and some nearby galaxies might be, if you're on a spiral arm, here we go, spiral arm, right? This side is travelling towards you, okay? So that side might be blue shifted, yeah? But if I'm receding away from you, oh gosh, it might be slightly blue shifted, okay? So nearby galaxies, the rotation of that spiral arm might still be blue shifted. And you can figure out how far away it is. But eventually, the further out you get, the recessional velocity becomes much, much greater than any rotational velocity, and we see that they're all redshifted, all right? So you don't find any galaxies blue shifted. The further away things are, the faster they're moving away from us. And that has some heavy consequences. The currently accepted... Oh, by the way, all of these measurements will have their own uncertainties. And so all of Hubble's constants all have uncertainties. And to this day, there are satellites that are up there spinning around, taking measurements and trying to recalculate Hubble's constant. Okay? And that's the problem. There is so much variation out there. It's not all linear, but it's pretty close. And you can, if you Google search Hubble's constant, there will be a massive table of all the different space organisations and scientific organisations that have had a crack at calculating Hubble's constant. And some organisations use certain types of stars because they might be a bit more reliable. Some organisations use certain observatories because they might have a bit of a relationship. Some might use certain methods opposed to others. So they all kind of hover around about 72-ish, plus or minus, okay? As I said, the further you are out, the irregularities are no longer apparent, okay? So, I'd like you to consider simplified units of Hubble's... Oh, by the way, I'm all over the joint. Just remember this is y equals mx, and so Hubble's law is v equals h naught d. That's Hubble's law. Okay? So Hubble's law, Hubble's constant is basically the gradient of that graph. It's the rate that describes the recessional speed as a function of distance from us. Okay? So, let's look at these simplified units. If I rearranged h naught, well, that's going to be your v over your d, I think, yes? And we'll use the equation 71 kilometers per second over megaparsec. Now, let's expand this out and convert. 71 kilometers per second over, now I'm going to use the megaparsec to the light year, and then the light year to the kilometre. Essentially, from the previous lesson, we said that a parsec was 3.09 times 10 to the 16. By the way, I'll just say it's going to be that multiplied by that. Well, actually, no, because we need a mega out the front. So there's our mega parsec in meters. And then I missed a per second there. So look at this. This is really going to be a bit confusing. Basically, everything under this line is coming from timesing these two conversions together. Okay? So we times those two conversions together. We get a cancely, and the unit is simply 2.30 times 10 to the negative 18 per second. Okay? So Hubble's constant is simply an inverse of time. Now I'm jumping to the next page because the next page is going to say Big Bang Theory, universe expanding, started at a really small singularity. Hubble's constant is the rate at which our volume of space, of the universe, is expanding. And basically he said that if we were to invert that rate, it would give us the time that the universe existed in zero space, and it's called a singularity, a single point in space with zero volume. That's T0. That's when the universe started. Okay? It's like extrapolating backwards. So, this is a really cool a really cool evidence to support the idea. T0 is going to be the inverse of H naught. So I'm just going to get you to invert that. Here we'll go 1 over 2.30 times 10 to the negative 18 per seconds. And we get 4.35 times 10 to the 17 seconds. And that is the age of the universe. but it's not a very good unit. So let's do some conversion. Let's divide by 60 to get it to minutes. Let's divide it by 60 to get it to hours. Let's divide it by 24 to get it to days. And let's divide it by 365.25 to get it to years. And we get 1.38 times 10 to the 10 years, or 13.8 billion years. Okay? So that is the current estimate. I think they're using 72 at the moment. If you use 72, it comes down to 13.4 billion years, plus or minus 5 or 8%, depending on which Hubble's constant you're using. So obviously there's a fair amount of uncertainty. I say uncertainty because we're looking at, it's not perfectly correlated. There is a bit of a spread. Okay? So imagine doing your minimum and maximum gradient method on that bad boy. Yeah? Your maximum and your minimum gradient might range from something to something, and that's how they're figuring out their uncertainties. Over the page. You could be asked for evidence of the Big Bang. Or sorry, evidence that supports the Big Bang theory. How about we just go evidence that supports the Big Bang theory? I have to say that it is a theory. It cannot be proven. No one was around back then and said, yep, singularity right there, and I saw it expand really, really fast. So it's all indirect evidence. So it will always remain a theory. Just like the flat earth theory and the turtle theory where the universe is on the back of the turtle Earth is on the back of a turtle that's swimming through...
Earth is on the elephants that's on the turtle that swims
through space.
Upwards at 9.5.
They are all theories. Some theories are more supported and more accepted than others. So we can discard those crappy theories. This one is the best. Because all of the evidence that that theory purports or puts forward has been confirmed. So the Big Bang Theory puts forward an idea and scientists go and test and observe and see if it's, yes, it's there, it supports it. So, the first thing is, the idea is, the further out you get, the faster the universe is expanding. Right? And so if you go back in time, it's going to collapse back into a singularity. So the idea is the entire universe must have come from a single point, billions of years ago. You might just want to add T0 is the inverse of Hubble's constant, which also supports it. Next, quick little story time. Back in the 1960s, there were two scientists, two engineers, radio engineers in fact, Wilson and Penzias. They were experimenting with a 6-meter radio telescope. This is a unidirectional, like your eyeballs. It can only look in one spot. If you want to look left, you've got to tilt your head left. If you want to look up, you've got to tilt your head up. So this thing could swivel up, down, left, right. And they were trying to measure wavelengths in the microwave range, okay? They were getting all of this background noise, all of this static, and they couldn't account for the static. It was there at all hours, day and night. It didn't turn off. Back in those days, radio stations would go to bed. Good night, everyone. Boop, they'd turn off. The TVs, good night, everyone. Boop, they'd turn off. Whereas nowadays, TV is 24/7. Back in the 60s, they shut off. They pointed it away from the town towards the town. It didn't matter. Down to the ground, up into the air. It didn't matter. They called the local military base and said, are you guys playing with radio waves of yay meters? No, we're not doing any of that. Okay. They couldn't figure it out. They climbed into the dish and they taped over all of the rivets, thinking that the little rivets of the bolts might be causing some interference, that the waves were maybe diffracting or reflecting. But no, they were too small. They scooped out dielectric material, pigeon crap, because pigeons would roost in the dish. So they scooped out all the pigeon poo, and still nothing was happening. From what they could tell, it had a few degrees, 2.7 Kelvin was the temperature. Because remember Wien's law? Wien's law says that lambda peak is Wien's constant over absolute temperature. And the absolute constant, I think it was 1.989 by 10 to the negative 3. And so let's just tweak this. They said, all right, it's about 2.8 Kelvin. And so the peak wavelength is 1.989 over 2.8. It's roughly that range, which is microwave. Okay, so that was the signal that they were tuned into. These guys didn't realize that they had just won the Nobel Prize in Physics. They took their info to a local university and said, guys, we've got this problem, we've got this background noise, we've got no idea where it comes from. And the physicists at that university said, that's remnants of the early universe, that's the Big Bang right there. And they didn't realize, because the model of the Big Bang says that we should currently be in a swath of electromagnetic radiation of a temperature of 2.8 Kelvin that corresponds to that wavelength of microwave. Okay? Here's the thing. After the Big Bang, there would have been tremendous amounts of high energy gamma rays and X-rays swimming around in that universe. But that universe that it exists in is expanding. And so all of that X-ray gamma ray is getting stretched out and stretched out. It eventually goes through UV, through visible, through infrared. And now we are currently at the time of the universe where it is 2.89 Kelvin. So it's been stretched out to microwave. Okay? So the model suggests billions of years later, this radiation should have been shifted to microwave. And sure enough, there it is there. That's all the background, cosmic microwave background radiation. And these two gentlemen were awarded the Nobel Prize for finding or detecting this. By the way, this radiation is approximately 13.8 billion years old, and it's racing through this classroom right now. And just swashing around you like radio waves. Because here's the thing, there's no edge of the universe. It was everywhere at the start, and so it's like running on a treadmill. You're moving, but the treadmill's getting faster, so you're slowly moving backwards. It's a bit of a tricky analogy, but it's here right now. It's racing through this classroom, 13.8 billion years old. Do you know your old school TVs that looked like this with the round TV and the big fat boxes like this, and you've got your old aerial like that? And if you weren't tuned into a signal, then you would just have static. Remember that black and white snow of an old school analog TV that's not tuned into a certain frequency? That around 2% of all of that noise is cosmic microwave background radiation. So you can actually listen to the sounds of the early universe. But not really, because 98% of it is all the muddled crap from all the other TV stations and radio stations. One last thing. In the early moments of the Big Bang, we are talking between 1 second to 1,000 seconds, so first 20 minutes. They were at a temperature where quarks could form hadrons, and hadrons could then be fused into other hadrons. So this, at the early stages, the early universe was acting like a fusion bomb, like a star. It was acting like a star, where hydrogen was fusing into helium. But think your gas laws. As your volume increases, temperature and pressure goes down. So after 1,000 seconds, it got too cold and the fusion process stopped. And so your scientists did all of the maths and said, all right, we've got all this matter and all this temperature and pressure. Fusion's occurring. Hydrogen's being fused into helium. After that, how much should be left and in what ratio? And so they worked out the sums, and it should be approximately a 3-to-1 ratio of hydrogen to helium. And so sure enough, you look out into the universe and you see a 3-to-1 ratio in all of the galaxies, 3-to-1. Do you remember when I said if we look at an emission spectra, sometimes it's more important to look at the relative intensity of emission spectra? And this is where this comes in. If you look with your spectroscope, you might see a relative intensity for hydrogen, And then you would see a relative intensity for helium. And it's always going to be 3 to 1. So this was a big one. The scientists looking at they're crunching the numbers with their calculators, using the model of the Big Bang, not looking outside, looking at their paper and their calculators. They did the maths and said, Big Bang theory says that we should be left, after the first 1,000 seconds, we should be left with a 3 to 1 ratio. And then the experimental astronomers went out and looked, and they confirmed. Everywhere you look in the night sky, you will see a 3 to 1 ratio of emission of hydrogen to helium, suggesting that we are in a universe that's mostly hydrogen, then helium, then heavier and heavier, you're getting less and less. Okay, so we are in a universe with an abundance of hydrogen and helium that the Big Bang Theory predicted. It's really, really interesting, and unfortunately we spend all of 3 lessons on it, and then I say, bye everyone, good luck. Come and find me at, what did I say? Come and find me at lunch or after school. I'll be hanging around. We'll put the solutions up. You can go through it. I'll be around lunchtime and after school. I'm sorry to be nasty, but I can't give 30 minutes for you guys to look at your test.